our discussion of Chapter 8. Chapter 8, the topic of Chapter 8 is viscous flow in pipes. And it's a really interesting topic for very many engineers. There are a lot of times where fluid moves through pipes, whether you're a civil engineer or a chemical engineer or a petroleum engineer or a mechanical engineer, or really any branch of engineering I can think of, with the possible exception of electrical or computer engineering. This is sort of a foundational piece of the puzzle. So we're going to cover sections 8.1 through 8.3 in this Vodcast, number 23. And then Vodcast number 24 will finish off Chapter 8, the topics that we need to cover. So let's get started. Let's go to the document camera. All right, so first of all, Chapter 8. When we talk about conduits, we are referring to all sorts of conduits, anything that transports a fluid. And we roughly divide conduits into two different classifications based on their cross-section. So round conduits are referred to as pipe, and non-round conduits are referred to as ducts. Now, almost all of the time, conduits are joined together in ways that move a fluid, often water, but not always, but are joined together in ways that move fluids from one place to the other. And we can have fittings and valves where we tee off pipes, for example. Like you may have water coming in this way, and you may have a type of a fitting that takes water off in this direction and in this direction, but not in this direction, for example. Or you may have a valve that can close off the flow here, maybe to divert the flow over here through a different sort of a fitting. And then you can also have pumps and turbines. Pumps put energy into a fluid system. An example of this is if you have a well and the elevation of the water surface in the well is lower than the elevation of the water surface in your house, you need to put energy into the water system in order to move it up to where it will run in your house. This is also why a lot of times you'll see, like here in Powell and in other towns, there will be water towers where water is pumped up to some elevation. The reason obviously there is that then you have a lot of elevation head and the water can flow freely regardless of the situation that's going on. So if you don't have an influx of water or if you lose electricity or whatever is the prime mover or the energy source for that pump, a water tower can help you overcome some of those, and especially at times of high demand, such as fire flows. If there's a fire, actually people's fire insurance rates depend on the amount of volume that a municipality can deliver to a fire through the fire hydrants as well as the fire trucks at times of high need. A turbine is something that just takes power out of a system, and in previous chapters 5 and 6, for example, we studied how Pelton wheels work. Pelton wheel is just a turbine that is spun by water and creates energy, for example. There's lots and lots of different examples. Now, one of the things that happens with all sorts of components in pipe systems is that the frictional contact between the fluid and the surface of the pipe or fitting or valve or appliance such as a pump or a turbine causes a decrease in energy of the system. So when we look at Bernoulli's equation, which is here written in terms of a head or in terms of dimensions of height of a fluid column, we know that the pressure head plus the velocity head plus the elevation head is a constant, except if we have a head gain, H sub G from a pump, or H sub L, which is a friction loss, which is a head loss from either friction, turbine, fittings, valves, etc. So one of the things that we do in this chapter is we're going to quantify, especially head loss. Head gain is generally given by the appliance itself. For example, if you have a pump, it will be rated at a certain number of horsepower, and you can convert that into an energy gain or a head gain. And so frictional losses it's convenient to report them in feet of fluid so that we have the same dimensions as we see here in Bernoulli's equation. All right, now kind of continuing with this idea. The term hydraulics technically refers to the flow characteristics of water, but hydraulics can also be used sort of loosely to describe fluid flow for many different types of fluid. And one of the distinctions, or one of the divisions that we make in fluid dynamics is we sometimes talk about hydraulics, and we sometimes talk about hydrodynamics. Hydraulics tends to be the study of fluids that comes from more of a boots on the ground or an empirical or a lab data gathered sense. And hydrodynamics is the stuff that is very, very intensely mathematical and comes from pretty rarefied theory. So the one thing about fluids that can be confusing to a lot of people, or maybe not confusing but confounding, is the fact that only a fully developed laminar flow of incompressible simple fluids is completely analyzable by methods of analytic math. And as engineers, this may come as a big shock because we're used to using math, analytical math, in other words, x equals fill in the blank, that kind of math, as our most important tool. And it turns out that only very simple flow regimes of very simple fluids moving in very simple ways are completely analyzable in this manner when it comes to fluid dynamics. A lot of types, and it doesn't mean we throw up our hands, there are other types of fluid flows that just require us to use tools of numerical methods, graphing, trial and error solutions, similitude, or modeling, where we take characteristics of a fluid flow and we replicate them mathematically, and then we extrapolate the meaning of that replication. So regardless of what industry you go to work in after you graduate from college, and really regardless of whatever field of engineering you go into, you will almost assuredly be using some sort of water simulation software or other fluid simulation software. So this is something in Chapter 8, we talk about the viscous flow of fluids in pipes. And we are really learning a vocabulary and a basis for understanding the way fluid moves. But when it comes to analyzing very complex systems, for example, if you were a water resources engineer and you were working for the city of Casper, Wyoming, the water system is very complicated and there are a lot of constraints. And I don't mean specifically Casper, any system is this way, where you have demands based on time and occupancy and unexpected situations like fire flows, and expected situations like in the summer people want to water their grass. And you have constraints where you cannot allow water to remain stagnant because it is no longer fresh. You can't let water stagnate for longer than certain periods of time. And you have to have a supply that meets your demands under a wide variety of situations. That's really not the kind of a thing that you would use a piece of engineering paper and a pencil and a calculator to solve. When you need to create an entire system like that, you're really going to be using modeling software. But the terms that you hear today and the basic methods of analysis and the distinctions that we make between different kinds of flows are the ones that you will hear over and over again. And the ones that you'll need to understand very, very well in order to use this kind of modeling software to its ultimate potential. So, talking about that, we divide it up all kinds of ways, because what we really try to do is to get to an idea of looking at a fluid regime, a fluid flow regime, in a way that we can eliminate the things that are no longer important to that flow. So one of the ways that we split flow up is whether if we have fluid flow in a pipe, we divide it up into whether the pipe is flowing full. In other words, if the fluid is all the way up to the top and covering the entire circumference of the inside of the pipe, or if we have a free surface. If you have a free surface, in other words, if the water is not completely filling up the pipe, you really have what's referred to as open channel flow. Because if you have a free surface, what that means is there's no chance for pressure to build up or dissipate, that the pressure at this side of the pipe is going to be the same as the pressure at this side of the pipe. That's because it's open to the atmosphere, essentially, even if it looks like it's inside a pipe. If you have a free surface, you do have that particular atmospheric pressure that is the same on both sides of the pipe. If, on the other hand, you have a pipe that's flowing full, the pressure at the two ends of the pipe, or as you move along the pipe, can be significantly different. Pressure at time 1 is not equal to pressure at time 2, and there can be, and almost always is, a delta P in the pipe. And the fluid behavior is significantly different depending on whether it is laminar, transitional, or turbulent. And we'll discuss these meanings, and we'll discuss a method of determining which one it is that we've already talked about, which is using the Reynolds number. The Reynolds number, as you recall, we talked about this, I think, back in chapter 5. But basically, the Reynolds number talks about the comparison between the inertial and the viscous forces of the fluid. And a high Reynolds number indicates that the fluid is somewhat chaotic and is, as we classify it, turbulent. Then if it's an intermediate number, it's a transitional fluid, and if it's low, it's laminar. Now, an exact number that determines whether the Reynolds number indicates that the flow is laminar, transitional, or turbulent is not real. You can't really say this exact number, above it it's turbulent, and below it it's transitional. Kind of depends on the flow regime, the type of fluid, and the piping system, or whatever conduit it's being moved through. But in general, unless you have better information, if the Reynolds number is below 2100, that tends to indicate that we have laminar flow. And if the Reynolds number is between 2100 and 4000, tends to be transitional flow, and if it's higher than 4000, it tends to be turbulent flow. And how you calculate Reynolds number, we'll do that a little bit later, but it is a dimensionless number, and it's something that is very common in terms of fluid behavior, and it's listed in several different places in your textbook. But if you take your textbook and you turn to the index at the back, and we look for Reynolds number, you'll see that it's listed at many locations throughout the book. We have a discussion of Reynolds number as early as page 20 and as high as page 430, plus some very specific ideas about the Reynolds number. So what I wanted to show you here is just that we have a ton of references to the idea of a Reynolds number. So if you go to the first occurrence, page 20, which is way back here, we can see that the Reynolds number is just introduced as a concept in example problem 1.4. And basically, we need to write it in units so that all of the units cancel out and it becomes dimensionless. So the Reynolds number value is given by rho, which is density, times the velocity of the fluid, times the diameter, and sometimes it's some sort of a characteristic length. It doesn't necessarily have to be a diameter of a pipe, although it often is, divided by the viscosity. And if you work the units out, that will, if you've got the units in a consistent set of units, that will come out to be a dimensionless quantity. Now, this number, this Reynolds number for this particular problem is 156. And we don't really make any judgments about it in this particular problem, this early in the text. But now we would know that that indicates that we are, frankly, in laminar flow. So, because if we look at our numbers less than 2100, let me come out a little wide, less than 2100 is laminar, and our Reynolds number for that problem was 156. All right, now there are two things that that govern these ranges. You know, is 2100 really the point of transition between transitional flow and laminar flow? Well, it depends on the characteristics of the fluid, and it also depends on the characteristics of the conduit. So that's kind of where we're going with the rest of this discussion. Now, one of the tests that is used to determine whether a fluid flow is laminar or transitional or turbulent is a test using a dye streak. And this is described in your book on page 445. And on page 445, we have a little, and this is actually a really classical experiment. But what happens in this experiment is we have flow entering a smooth, well-rounded entrance. So the well-rounded entrance just prevents any entrance effects or minimizes entrance effects. And somewhere where we're in completely developed flow, when we're away from getting any of the entrance effects, we have a small pitot in which a dye streak is emitted. And if you look at the shape of the dye streak as it moves from the tube of it, where it enters, you'll see that the dye streak looks significantly different depending on whether the flow is laminar, transitional, or turbulent. And that dye streak really indicates what all of the layers of fluid are doing. So in the top picture, you can see that we have laminar flow. The dye streak, as the fluid moves, just remains unblurred and steady in a straight line. The transitional flow, the dye streak originally looks like that, but it's a little blurry, and then it gets a little bit bumpy. And finally, if you have a large enough Reynolds number, and you have this situation where the dye streak is extremely blurred, and you have, if you think about it, this gives you an indication of the velocity of the fluid. What you see here is that the velocity of the fluid is not moving in a primarily x direction, that we have velocity bumping up and down. We have this irregular and somewhat chaotic velocity pattern that indicates turbulent flow. So, in general, if we talk about fully developed laminar flow, which is the type of flow for which we have the most analytical math, we can take this entrance length, which is how far it is before we get into fully developed laminar flow from the entrance of a pipe. Just go ahead and draw this for you. So what we can say is that if this is the diameter of the pipe, and we're going to have some distance L sub e. We don't know what that is. That's what we're looking for. But this ratio is going to be 0.06 times the Reynolds number for laminar flow, and it's going to be significantly different for turbulent flow. You can see that the constant is bigger, but we also have Reynolds number to the 1/6 power, which means that for turbulent flow, the Reynolds number becomes less of an effect. In other words, it's less important to find out how far it is we're going to have to go into the tube before we get to that fully developed flow if we are in turbulent flow. All right, so, and just to continue with that, the L sub B over D is called the dimensionless entrance length. All right, now the differential of pressure with respect to X, in other words, the pressure gradient, is going to be the very largest right at the entrance. And so that's really what we're getting around when we go to this idea. We want to get into the part of the flow where the del P del X is more or less constant. And what you see is if we take this line that is the slope of the pressure drop versus the distance from the entrance, as we get closer and closer to the entrance, that pressure drop goes up, doesn't it? just indicating that it's higher than you would expect here. And those are just referred to as entrance effects. So we want to get away from the entrance effects before we can talk about fully developed laminar flow. So that's the kind of flow that we're analyzing in this section, is laminar flow at this L sub E or greater away from the entrance to the pipe. All right, so if we continue talking about this idea, laminar flow characteristics are different than turbulent flow characteristics. And most turbulent flow is chaotic. And that just means it's pretty much unanalyzable in the strictest sense of the word, or in the analytical math sense of the word. It's generally the subject of simulation or computational fluid dynamics. And computational fluid dynamics, or it's just abbreviated CFD, is a graduate and postgraduate field of study. So there's a lot of different fluid regimes that people are spending a lot of time analyzing, looking at different patterns of how fluid moves and relating them to other patterns of different types of fluids that move. So those are just some ideas that that will kind of limit what our discussion is about today. All right, so in section 8.2, we're discussing this idea of fully developed laminar flow. And we start with, and I'm not going to drive these equations for you too much, I'm just going to reference it. We're really starting from Newton's second law of motion, that force is equal to mass times acceleration. And if we look at that for a fluid element, what we find is that as fluid moves through a pipe, and we're talking about laminar flow, but what we see is that at the edge of the pipe, where the first little lamina of fluid touches the pipe, that we have a velocity equal to 0. And that is referred to as the no-slip condition. Right? The next lamina moves a little bit faster, but it slides against the lamina at the edge of the pipe. And we continue onward to where we have a 0 velocity at the wall of the tube, a maximum velocity at the center line, and the shape of the velocity profile is essentially parabolic. So we have the velocity is some sort of a function of the radius of the tube, where the velocity is a maximum at the center line and the velocity is 0 at the wall. Well, because these little lamina of fluid are flowing against each other, they're moving at different paces and they're pulling. The lamina at the wall is pulling the next lamina back, and the lamina away from the wall is pulling the lamina at the wall ahead. What happens is that this is basically a description of the viscous forces in the fluid. It's the desire of the fluid to sort of adhere to itself. And this viscous force causes shearing stress, which is designated by the Greek letter tau. So we look at the pattern that tau, because velocity, if you see, is a function of the radius, so is tau. And the nature of the function is that tau at a particular distance from the center line is equal to the tau at the wall, where it's a maximum, times the radius over the inside diameter of the pipe. And so tau, velocity is maximum at the center line, tau is 0 at the center line, and tau is maximum at the wall. So if we have a situation where the length over the diameter of this pipe, this ratio, is much greater than 1, we'll have a delta P, or pressure drop, equal to this term. And this is one of the basic pipe flow equations. And it just discusses the balance between the viscous and the pressure forces. So we have viscous forces, more or less, and pressure forces. So we see how they relate to each other. Now there's an excellent picture in your textbook on page 451 that shows these relationships. This is a pipe with an idealized fluid. This is the Tao profile, where Tau is a maximum. Here, Tau is 0 at the center line. And you can see that it's a linear relationship from wall to center and then back from center to wall. The velocity profile is parabolic. And then if there were no viscous effects, this slug type of a profile, a constant profile, is what we would expect to see for our velocity distribution. All right, so this brings us to sort of the heavy hitters. We have some equations that are hugely important in terms of laminar flow. And the French, there were two guys that came up with these at different times, but they are referred to as the Poiseuille, or sometimes they'll be called Poiseuille, laws for laminar flow. But there are actually two independent scientists that worked at different, they were sort of contemporaries, but Hagen and Poiseuille both came up with these ideas. And so type of fluid that's governed by these equations, in other words, fully developed laminar flow, is sometimes referred to as Hagen-Poiseuille flow. So these equations for velocity and flow rate are true for fully developed laminar flow, where we have velocity is equal to the pressure, the delta P, the pressure drop or the pressure gain between 2 points in a pipe or a conduit. This is actually for a pipe, but in other words, it has to have a round cross-section for this to be true, minus the specific gravity of the pipe times the length times the sine of the angle. That would be the angle that the pipe makes with the horizontal. So in other words, if it's 0, that would be 0 times d to the 4th over, that would be the diameter of the pipe, 32 times viscosity times the length of the pipe again. And all we've really done here for Q is multiply through by a cross-sectional area. So we have a slightly, you know what, this is, I was looking at this and this was bugging me. This is to the 2nd power, because then we multiply by pi d squared over 4, and this is to the 4th power. So the expression for volumetric flow rate involves d to the 4th. The expression for velocity involves d to the 2nd. Okay, and you can get the same results in a couple of different ways, which is the what they do in the rest of the chapter. Makes for interesting reading, but it's just a different treatment that arrives at the same point. We can get the same result using our old friend, the Navier-Stokes equation. We can also get it using dimensional analysis. Right. So let's go back and talk about kind of a ginned up Bernoulli type equation. Now we talked about before, when we discussed Bernoulli, I had mentioned to you that the Bernoulli equation is often used and also is often misused. So if you look at this statement without the coefficients alpha, you'll see that I have a form of the Bernoulli equation where we have pressure head, velocity head, and elevation head equal at different points in the conduit. And that is a statement of the Bernoulli equation. What it's saying is energy is conserved. But it turns out not so simple. There is kinetic energy that's lost due to these effects of shear, and also due to the roughness in the pipe. So we call those constants alpha 1 and alpha 2, and we refer to them as the kinetic energy coefficients. So we can quantify, and this is a somewhat empirical quantification of the head loss, which we discuss later, which is the feet of fluid of energy that we lose. Turns out that it's a result of the viscous forces and the length that we flow through the pipe, and also, of course, the specific weight of the pipe. So this is an equation. We can just tack it onto the end, because if you think about it, we start out with a certain amount of energy, and we end up with that same amount of energy after we account for the head loss. So you could also say head loss is equal to the energy at time 1, or at the beginning of the flow, minus the energy at the end of the flow. And either of those is an equally correct way to think about head loss. All right. Now, in section 8.3, I guess I've kind of talked about this already. I want to save 8.4 for the next lecture. But I want to make a couple of other points before I work out the homework problems so that we can, let me see about this. I guess I can, all right, I'm going to put these over here. But I want to make another couple of equations. I want to put them into the front of your mind. As we transition from laminar into turbulent flow, we can take a look at what this Tao profile looks like, and it really becomes very complicated. There are some diagrams in your textbook that are very interesting. However, there's not really very much that is of serious use in this section in terms of computational fluid dynamics, or not computational, but empirical fluid dynamics like we're doing right now. But I do want to bring your attention to two forms of an equation, or one equation and a simplified form in section 8.3 on page 475 of your textbook. The equation that I'd like you to reference is a very famous and widely used fluid dynamics equations called the Darcy-Weisbach equation. And Darcy is a French civil engineer whose first name was Henri, or Henry, as most of us would say. And engineer Darcy developed some equations, especially for radial flow, that are extremely important in terms of homogeneous petroleum reservoirs. But the main equation that he wrote is, or there's many, many equations that he wrote, but let's just get down to a couple of these. We know if we take a look at a pressure drop in a pipe, we can rewrite Bernoulli's equation in a form that looks something like this. So we've kind of changed units. We're now in pressure units, aren't we? Instead of fluid feet units. And if we continue with this, we have an empirical solution to what this head loss looks like based on the ratio of length to diameter and based on something about the kinetic energy. This is a rho, not a pressure term, and something called a friction factor. Now, a friction factor is something that you can pick off of a device called a Moody chart. And we're going to discuss the Moody chart in the next vodcast pretty carefully, because friction factor has different correlations with pipe roughness and also with the Reynolds number, and depends on what type of flow we have. So we'll talk about that in just a few minutes. But for now, what I would like you to get out of the Darcy-Weisbach equation is that if you have a horizontal or an inclined pipe, that the head loss for most types of flow is going to look like this. And this is going to be in feet. Okay? This is for a horizontal or an inclined pipe. If you have, and you can incorporate that here, and it just makes it look, and it just is this, isn't it? So this is for a horizontal or incline. Now you can use this in all cases. However, if you think about it, in the situation where you have a horizontal pipe only, the Z2 minus Z1 is equal to 0, or Z2 is equal to Z1. And so the expression for pressure drop, delta P, which is just P1 minus P2, can be reduced to this friction factor times the ratio of L over D times rho V squared over 2. And I just want to point out that we have V squared over 2G, and that there is a relationship between gamma and rho, where this is density and this is specific weight. So rho times G is equal to gamma, and that's why this is essentially equivalent, or inherently or something equivalent to this. All right, so this is only for a horizontal pipe because we've eliminated Z2 minus Z1. And this is the Darcy-Weisbach equation, which is either horizontal or on an incline. All right, so that gets us through the end of the material that I wish to cover in section 8.3. And so at this point, I would like to work out problems 8.4 and 8.29 for your edification to get started on your own homework set for this chapter. So problem 8.4 is in your textbook on page 521. And if you read through 8.4, this is what it's asking us. It says we have air that exists at 100 degrees Fahrenheit, and it flows at a standard atmospheric pressure. That would be approximately 14.7 psi in a pipe at a rate of 0.08 pounds per second. Now that might be a mass flow rate, or it might be a flow rate of weight. The way that this is written is a little bit indeterminate, but it's going to turn out to be the same number and the same value, because a pound of mass weighs a pound of force. Determine the maximum diameter allowed if the flow is to be turbulent. Okay, what's it really saying? Well, what it's saying is that if you have a small diameter, the fluid will move faster and the motion will be turbulent. If you increase the diameter, the velocity will slow down and you will have a more laminar flow. So they want us to at least have whatever diameter is going to be required to keep this in the turbulent flow range, which I've said, if we don't have better information, can be considered that we have a Reynolds number of greater than 4,000. So that's our criteria for this problem. So what we want to do is to calculate for this flow of air at 100 degrees, what values of rho, V, and mu will keep R sub B at 4,000, what diameters will keep our R sub B value at 4,000. So the first thing that I will do is I'll take a look at some of my relationships. Well, I could solve this for V, just rearrange my variables. Then remember that Q, or volumetric flow rate, is equal to volume times area, and since it's a round pipe, a round conduit, the area is going to be pi d squared over 4. And this d is what I'm looking for. That's the d that's going to correspond to a Reynolds number of 4,000 when I start plugging numbers in. So I solve this out, and what I find is that Q equals V times A is 1,000 times the viscosity of air at 100 degrees Fahrenheit times the constant pi times the diameter divided by the density of air. All right, so using a mass flow rate of 0.08 pounds per second, my gamma times Q, right, my specific weight times volumetric flow rate is mass flow rate, or I can say that gamma is also equal to G times rho. Plugging those things in, and also right here I'm having to assume, in order to get my rho, I'm assuming that gas behaves as an ideal gas. Now if I had more data, I might be able to make a better assumption, but air at 100 degrees Fahrenheit is pretty light. So ideal behavior is not unreasonable. All right, so I solved for my density of air at those conditions, standard atmosphere, converted into feet, the R value for air, which I looked up in my textbook, and the temperature of air in degrees Rankine, and I compute a value of rho of 0.0022 slugs per cubic feet. Okay, now the one thing I want to point out is this is the correct way to do it, but I knew that my volumetric flow, or my flow rate, which I didn't really know was a mass flow rate or a, I don't want to go into that. Never mind, just forget that. It gets kind of confusing. So let's just do it that way. We've done everything correctly, we've converted properly, and we know what my density is. All right, I also know from the two equations on the past page that if I take my mass flow rate and I divide it by rho times g, that I will come up with some sort of a Q. So I need to look at my numbers, and here I have a pound, here I have a slug, and here I have feet per second squared on my acceleration. So if I take a pound per second, and down here, this foot cancels this, I get slug in the bottom, and then I have feet squared, which flips up to the top, and second squared, which flips up to the top as well. All right, I don't really know about this, but let's talk about my slug. I know that one slug, this is from Newton's second law of motion, weight is equal to mass times gravity. One slug accelerated at gravitational acceleration of 32.2 feet per second squared equals 1 pound of force, right? So I can write slug as being a pound of force second squared per foot. So to look at my conversion, oh, I left a second down here, so that's actually like that. Okay, and then I have my slug, which instead of writing as a slug, I'm going to write as a pound second squared per foot. And you can see then that pounds cancel, foot squared is foot to the third, and I'm left with a second. This cancels against this on the bottom. So I get a cubic feet per second, which is a good unit for volumetric flow rate. So I find a value of the viscosity of air at 100 degrees in table B3 of my textbook, and here's that value. And so I can compute Q, or I can find out, I know that Q is equal to this, and I can solve that equation for D, which is what I'm looking for. All right, so then I just plug in my values, and I come up with 2.01 feet. Therefore, to remain turbulent, the diameter of the pipe must not exceed 2.01 feet. All right, then next we have problem 8.29. 8.29 is on page 523 of your textbook. 829, right here. We'll come in a little for a close-up. All right, and we have another gas. We have carbon dioxide at 0 degrees centigrade and a pressure of 600 kPa absolute, flows through a horizontal 40 millimeter diameter pipe with an average velocity of 2 meters per second. Determine the friction factor if the pressure drop is 235 newtons per meter squared per 10 meters of length. Okay, a great or a slight simplifying assumption here is that we know, it's not an assumption, but a simplifying condition is that this is a horizontal pipe. That means that we do not have to use the full-blown value of the Darcy-Weisbach equation. It means that we are able to use the simplified version of the Darcy-Weisbach equation for horizontal pipes only, which is, let me push this out. what we wrote down a little bit earlier, that delta P is equal to the friction factor times L over D rho V squared over 2. All right, so we basically just solve that equation, the horizontal version of Darcy Weisbach, for the friction factor. We need to get rho. Once again, we're assuming ideal behavior. We come up with a value of rho of 11.63 kilogram per meter cubed. We then plug in, I've got a hole punch here, sorry. This is my friction factor. It's equal to 2 times the given delta P times the given diameter, which I'm expressing in meters, over rho, which I calculated from the ideal gas law, times the velocity squared times the length, because we're told that this pressure drop occurs per 10 meters of length. And when I finish this off, I come up with a value of 0.0404. And as you work out those units, you find out that it is indeed dimensionless. All right. Well, that's it for this this Vodcast number 23. We've covered sections 8.1 through 8.3, and your homework is posted on the website, on the Moodle site. So I'll join you back here for our Vodcast 24, where we finish off chapter 8. See you then.